Thank you for having me. Have you ever looked up at the stars at night and wondered what the universe is made of? What are the fundamental laws of nature? Or how we got here? Well, these are big picture questions that date at least as far back as the ancient Greeks, and inspired me to become a physicist when I was a little kid. So I'm going to tell you what we've learned about these questions over the last century, and what remains to be uncovered about these deep mysteries. I'll start by setting the stage in the year 1900, at which point physicists widely believed that we were in the process of wrapping up our understanding of nature. As summarized in this, that's right, as summarized in this famous quote by a famous physicist, Lord Kelvin, who said that there's nothing new to be discovered in physics right now. This offers an important lesson. Never trust the Lord. The picture that he was talking about is what we now call classical physics, or Newtonian physics after Isaac Newton. It's basically the physics of billiard balls. Objects move around, they exchange energy and momentum. It's a fantastic theory if you're interested in describing the motions of projectiles or celestial objects or spinning tops. But then just 5 years later, in his Annus Mirabilis, his miracle year, Einstein obliterated every single thing we thought we knew about how nature operated in a series of some of the most brilliant papers ever written. And that included special relativity, which included his famous E's and MC squared, laying the groundwork for quantum mechanics, and even establishing that matter is made of molecules to boot. Special relativity is a bizarre theory that says that if you could travel on a spaceship and approach the speed of light and travel around for a while and come back to Earth, you'd find that less time would have elapsed for you than for the people on Earth. Your children could become older than you. This is a real effect that's actually been measured, and that really dramatically altered our understanding of the way that space-time operates. That theory was then further extended to general relativity, the theory of gravity, which says that massive objects like the Earth distort space-time, and what we observe as a gravitational pull is actually the manifestation of this distorted space-time, causing the paths of objects like the Moon to deviate, and that's why the Moon orbits the Earth. Just a few years later, Hubble would make measurements of nearby galaxies and find that all of them are receding away from us. That only makes sense if the universe itself is expanding, which has a really profound consequence, because if the universe is expanding as you go into the future, it must be contracting as you go into the past. That means that the entire universe, everything you see around us, emanated from a tiny point, and that was the Big Bang. In the 1970s, a series of brilliant measurements by Vera Rubin showed that galaxies are spinning much too fast near the outer edges. And without unseen mass to exert gravitational pull on the stars along the outer edge, you'd expect them to be flung out into the far reaches of space. And this was the first evidence for dark matter. A couple decades later, we made measurements of supernovae, which are exploding stars. They're so bright that we can see really far away, which means we can see into the past because the light took a long time to get here. And what we saw was that the universe was expanding slower in the past than it is now. That means that the expansion is accelerating, which makes no sense because gravity is always attractive. Going all the way back to 1905, back to the miracle year, Einstein was able to explain the behavior of electrons that get ejected from a metal when you shine light on it, called the photoelectric effect, by positing that light behaves like a particle, which is bizarre because we've known for centuries that it behaves like a wave. It's not a wave, it's not a particle, it's a wavicle. That's one of the cornerstones of quantum physics. Rutherford would then peer inside the atom with a so-called scattering experiment in which he bombarded atoms with particles, most of which passed right through because atoms are mostly empty space. Every once in a while they bounce off the nucleus. This is how we learned that atoms are made of nuclei with electrons whizzing around them. A series of measurements made at particle accelerators allowed us to then further explore the subatomic scale. What you're seeing here is the Atlas detector. This is the detector at a collider in Switzerland where I've been working for the last 15 years. And to get a picture of scale, that's a person. That's seven stories tall. And measurements made at colliders over the first half of the 20th century elucidated the structure of the atom, showing that the nucleus itself is made of smaller particles called protons and neutrons, which you've probably heard about. But maybe you're not aware that protons and neutrons are themselves composed of quarks, which are even smaller. Quarks and electrons, as far as we know, are the smallest pieces of the universe. And this table here, which kind of reminds you of the periodic table maybe, but every single particle in this table is elementary. There's nothing smaller inside of these particles. The Standard Model is a banal title for what is the single greatest scientific achievement of humanity. Scientists are really bad at naming things. And this particle over here you might recognize, this is the Higgs boson, the so-called God particle. Here you have a picture of an actual Higgs boson candidate that was recorded with that Atlas detector, which functions like a camera, and this is like a snapshot. And I'm immensely proud to have been on the team that, just one of the two teams that discovered the Higgs boson, leading to the 2013 Nobel Prize, and for which we also received a $3 million breakthrough prize last week, awarded to us by, of all people, Jeff Bezos. The Standard Model makes up 5% of the universe, and we understand it really, really well. The rest is made of dark matter and dark energy. We've measured how much of it there is, and we know that quite precisely. We have no clue about its nature. We have no clue about its origin. We have no clue about the underlying theory of which it's a part, and that's one of the major open questions. As for how the universe works, well, as best we can tell, it works according to the laws of quantum mechanics at the smallest scales, describing atoms, and it works according to general relativity at the largest scales, this describes gravity. But our goal is not to have two separate theories. We want a quantum theory of gravity that combines them into a single well-understood theory of everything, like string theory. As to how we got here, well, 14 billion years ago there was a Big Bang, followed by a period of rapid expansion. The universe expanded and cooled, the evolution being driven by dark matter, which slows the expansion, and dark energy that accelerates it. 14 billion years later, I'd say, things are going pretty well. And this is my entry into the global competition for the greatest photograph humanity has ever taken. Every single dot here is not a star, but a galaxy with hundreds of billions of stars. The pink, that's where the luminous matter is. That's where the stuff that you can see is. And the blue is where the mass is. The fact that the blue is displaced from the pink is proof of dark matter. And I want to conclude with a note about my personal idol, Albert Einstein. Not only one of the two greatest physicists of all time, along with Isaac Newton, but a lover of music and philosophy, great humanitarian, outspoken civil rights activist at a time when that was not really a thing. And he took this speaking engagement at Lincoln University, although he was very ill at that point, insisted on speaking to them. And if you have a chance to look at that photograph, note the faces of respect and also the laughter, because it looks like he just cracked a joke. So his name is Albert Einstein, and we shall not see his like again. Thank you so much.